This is the lesson for dot product 9.1. And in this lesson, we're going to do two different things. The first thing we're going to do is we're going to figure out how to compute what is called the dot product. This is just an operation, kind of like how addition, subtraction, multiplication, division, and many other properties and things that we do. This is dot product is a process that we do, and we're going to learn how to do that. It in itself is not something that we has a meaning. It's that this is an operation we use to find meaning, and that's the other part of our lesson, which is the two uses for this dot product. Why we need to know how to compute the dot product. Well, one of the uses is to figure out the angle between two vectors, and especially a special case where we specifically want to know if the vectors are perpendicular. But there's another word we're going to use with vectors, and that is orthogonal. Now, that word orthogonal is not just for vectors. This is just another word that means perpendicular, and this is the more mathematical term we use. The other use for the dot product is to find something called work when two vectors act upon an object. So these are these two parts are what we're here to do, and then the uses have two cases, two parts to it. So what is the dot product? Well, we have two vectors, vector u and vector v. By the way, in this, vector u is not a unit vector. It's just a vector called u, okay? To find the dot product, and we write it this way. Now, we don't write it with a pink and black. I'm just showing it's a big dot. It's not a tiny little pinprick dot like we do for multiplication. The dot product is specific to vectors, and it's not multiplication. Although you are doing some multiplication, but you will do both multiplication and addition to find a dot product. And what we do is we take the components for each of the two vectors, a sub 1, b sub 1, and a sub 2, b sub 2. We multiply the a's, so a sub 1 times a sub 2, and we multiply the b's, and then we add them together. And that is the dot product. That's how you find the dot product. Now, if you look at this, you're going to take two components and multiply them, two components and multiply them, add them together. What you will get is not a vector, and that's very important. You will not get a vector when you do the dot product. What you will get is a number, a single number. Now, what is that number? Well, it isn't that number has meaning. It's just that this is a property an operation that we do on vectors to get this number. And this number will be used, and we will find meaning in the things we use it for. We need to know some properties of dot product, different things that happen with that operation. And one is, it is commutative, meaning u dot v, and that's how you read this, u dot v is the same thing as v dot u. It doesn't matter the order of the dot product. And it's not multiplication. Do not call it vector multiplication. It's called dot product, okay? In this case, I'm adding two vectors, which would be a different vector. So this could give me some vector p of u plus v. And I'm going to have a vector, and then I'm going to take that resultant vector and dot w. This is the same thing as if I kind of just, it's not distribution, but it's very similar to it. I am going to do the dot product to u, the dot product to v, and then add that together. So once again, I'm going to end up with a dot product, which is a number, plus another dot product, which is another number. When you add two numbers together, you get a number, and that's the result of this is a number, okay? Here I've got a scalar times one of the vectors. So this could be like 3u or 2u, or I'm multiplying one of the vectors by some scalar. And then I'm going to do the dot product with another vector. This property says, well, if I'm doing a scalar times u dot v, I could just change that scalar. Instead of the scalar times u, I could have the scalar times v. And so it would just be the vector u times, so if it was 3u dot v is the same thing as u dot 3v. But what's really interesting with this also is you can factor out that that scalar, and then just do the dot product of u dot v, and after we get a number for this dot product, multiply that number times the scalar. which is much more convenient most of the time to do it this way. Now this, of course, means magnitude. The magnitude of u, which we know is a number. We're going to have the magnitude, and we're going to square the number. To do the magnitude, remember, it would be a squared plus b squared, take the square root. But we also notice that, well, the magnitude squared is the same thing as u dot u. Okay? So if we think about that, what that would end up with is a sub 1 times a sub 1, which would be a squared, plus b squared. B sub 1 times b sub 1. Let's do a few problems here, some examples. And we're using the vectors up here that are given in the problem, that vector u is 4, 1, and vector v is negative 2, 3, and vector j is negative 1, negative 2. For problem number 1, u dot v, I write both my a's. 4 and negative 2, I write both of my a's. I write both of my b's, 1 and 3. Multiply my a's, multiply my b's, and then add it all together, and I get the number negative 5. We do the same thing in problem number 2. We multiply our a's, multiply our b's, and then add them together, and we get negative 4. Now for this one, we're going to show it for this problem number 3, we're going to show it two different ways. First of all, what I can do is I can distribute that vector u and have vector u dot v plus vector u dot vector j. We've already done u dot v, so that's kind of convenient. Now we just need to do u dot j, and so we look up at the top and we look at our vectors and we multiply our a's, multiply our b's, add them together, and we end up with negative 5 minus 4 minus 2, which is a grand total of negative 11. But what if I didn't want to distribute this u? The other method I could have done, we're going to do it over here in the margin, because I want you to have both ways, because which way you do it is whatever way is easiest for you. And this time what I'm going to do is I'm going to add the vectors v plus j, because that's what that says. And when I add two vectors together, I'm going to get another vector, which is why I changed this to these brackets, these pointy parentheses, because we're going to get another vector. So vector u is 4, 1, and this here that I wrote in green is the addition of vectors v and j. So if we went up to the top and added our a's and added our b's, we get negative 3, 1. Now I'm going to do the dot product, multiplying 4 times negative 3, and multiplying 1 times 1, adding them together, and I get negative 11. The same exact thing. Which method should be used? It doesn't make any difference. Whichever method you find easier for the particular given problem. Okay. Problem number 4. Well, we're going to do the dot product of j and u. Here it is. And then multiply it by that scalar. We could have done 3 times j and multiplied j times 3 right away and then dotted it with u. But don't, this is not distribution where it's 3 times j and 3 times u. It's not. There's only one scalar here, number 3, this number 3. And so that's why, to me, it's actually better if you pull the scalar out, do the dot product, and then multiply the dot product times the scalar, so you don't accidentally multiply both vectors, because it's not multiplying both vectors. In number 5, we've got the magnitude squared, which is just u dot u. So I just do 4 times 4 plus 1 times 1. Remember, this is saying a squared plus b squared, and we end up with 17. And remember that this also means that the magnitude of u was the square root of 17. So you could say, oh, wait, if the magnitude is the square root of 17, then the magnitude squared is just 17. Number 6, we're going to do it two different ways. The first way we're going to do that is going to say, oh, we've already done the magnitude of j times v. You can see that up here is negative 5. Negative 4, which we did in problem number 2. And we've already done u times v, which we did in problem number 1, which was negative 5. So we've got negative 4 plus negative 5. So this one was actually very simple to do because we'd previously done those dot products. But we could have, if we didn't have that already done, I can see this problem that both of these are a dot product with v. So instead I'm going to add the two vectors together, and then do the dot product, and I still get -9. Again, it's just different ways to do the same problem. Now we're going to get the dot product theorem. So this is a theorem that's going to show us what we use the dot product for. There's a purpose in doing the dot product, and it's not just the dot product itself. It's that it lends itself in a theorem to find other things. So the dot product theorem says if we've got a theta, some angle that's between two non-zero vectors, meaning they have to go somewhere. I've got vector u, and I've got, here it is. It's a non-zero because it actually moves. And then I have another vector v, and there it is v. These two vectors have an angle between them, and the angle is always less than 180 degrees, or 180 degrees or less. So we don't call this outside part here the angle between the two vectors. The angle between the two vectors is the angle that is less than 180 degrees, and so there it is, theta. Okay? And if we have this, we have to have this configuration, two vectors. And remember, you can move your vectors so they both have the same initial point, and then you'll have an angle between them. We get a formula that says the dot product, which is what we learned how to do. The dot product is the magnitudes multiplied times cosine of the angle between. And that is the dot product theorem right there. That is the part that is called the dot product theorem. We can use this theorem and rearrange it and solve for theta. Well, what do you mean? We didn't solve for theta, we solved for cosine because we just divided by the magnitudes multiplied. But I'm going to take it up here at the top of my page. Here it is. What we're going to now do is we're going to take the arc cosine, or the cosine inverse of both sides, and when we do that, we have solved for theta. So this, using the dot product theorem, which says the dot product is the magnitudes multiplied times cosine theta, the angle between vectors u and v. But we can use the dot product theorem to solve for theta. Be aware, this is not, when we say theta equals, this itself is not the dot product theorem. It's how we rearrange it and solve the dot product theorem to find an angle. So we find the angle between. Let's do that for two problems. We've got two vectors, and we know that from that formula that because they want the angle between, I'm just going to write this down here and say, oh, we know that theta is the arc cosine of the dot product divided by the magnitudes multiplied. So we need to know the dot product. We find the dot product is 8 minus 15, which is -7. We find the magnitude of u, which is the square root of 29. We find the magnitude of v, which we get as 5. And then we just plug all of these things into this formula. And there we have it. The dot product divided by, I take the magnitude of 5 times the magnitude of a square root of 29, and I plug that into my calculator, and I get the angle of 105.068. We do have to recognize, whoops, I didn't mean to do that. These angles that when we get arc cosine, it should always just be exactly what it is that will, we should get a positive angle that is always less than 180 degrees. For problem number 2, well, we know this is what we're going to use. We're going to use this formula. And to use the formula, we need the dot product. We need the magnitude of u and the magnitude of v. So the dot product of u dot v for this particular problem is -6. The magnitude of u is the square root of 17. The magnitude of v is 2 root 2. Make sure you're simplifying. So now we're going to take all these numbers, plug it into the formula. And we have the arc cosine of -6 over 2 root 34. I did multiply these two together to get that 2 root 34 because we are multiplying our two magnitudes. I'm going to continue simplifying this because if I ask for exact answer, you would have to leave it in this form simplified, which would be arc cosine of -3 over the square root of 34. That would be the simplified if I asked for exact answer. You would take your calculator, plug this into your calculator, and you get the answer of 120.964, rounding to 3 decimal places. All right, This brings us to the special case of angles between, and that's orthogonal vectors. There's many times in applications and stuff we want to know if the vectors that are acting upon some object, like if it was me and there was the wind and there was some other vector, are the two vectors perpendicular to each other? So orthogonal means perpendicular. And remember, we use this symbol for perpendicular, so this symbol will get used in many times in problems. And perpendicular also means the angle between the two vectors is 90 degrees, or if we were doing it in radians, it would be pi over 2. So when we have two vectors where the angle between them is 90 degrees, we know that they are orthogonal vectors. So let's look at this for a second. Just think about this. If I knew the angle was 90 degrees, cosine of 90 degrees is 0. So I'm thinking about the dot product theorem, and I know that cosine of 90 would be 0, and this cosine of 90 equals the dot product divided by the magnitudes. The only way for a fraction, and this fraction right here, to equal 0 is if the numerator were 0. Well, the numerator is the dot product. So anytime the dot product is 0, I know I have orthogonal vectors. I'm going to have this situation. So anytime my dot product is 0, my vectors will be perpendicular. So let's do this. I want to know, are they perpendicular or are they orthogonal? Well, I do the dot product, and I find that my dot product, well, it's definitely not 0. I actually don't even care what it is. It's not 0. If it's not 0, then the vectors are not orthogonal. If you wrote the word perpendicular, I wouldn't mark it wrong. I do want you to get used to using the word orthogonal for vectors. For problem number 2, we go through the same process. We find the two vectors. Well, here, since they are written in their linear combinations, I'm going to write them in their component form so that I can do the dot product easier. And I take the dot product, I multiply my a's and I multiply my b's and add them together, and I get 0. So therefore, these two vectors are orthogonal. What's the other application? We said there were two different kinds of applications. One was to find angles between two vectors, and the other was to do something that is called work. So the other use of the dot product is when we do something what is called work. And work is a very specific term in physics that is a unit of a measure. It's a number, but it's a unit of measure that describes the amount of effort it takes. If you want to think of it that way, that work is the amount of effort. And the units are things like foot-pounds and things like that, it's a unit of measure that describes effort. Okay, so it's a quantity, one number. And we realize that the vectors that we're going to be using for the dot product, they're very specific. Excuse me, let me move that. They're very specific vectors, and one of them is a force vector, and the other one says in moving along another vector, which we use the letter D. The name of a moving along a vector is the displacement. This is like the cotton ball that got blown. It would be the displacement vector of where the vector started to where the vector ended. Okay, and that's going to be work when we do the dot product of these two vectors. So work is the dot product of force and displacement. And I want you to write down this sentence on your notes, and it's the quantity work is the dot product of force and displacement. And force is a vector, displacement is a vector. So here's our first example. A force is given by this vector 2, 3, and it moves an object from 1, 3 to 5, 9. Those are points, okay? So we need to find that other vector. This moving the vector from this point to that point, that's the displacement vector. So we've got the force vector 2, 3. And the displacement vector, and we use these 2 points, we find is 4, 6, because we went from 1 to 5, which is 4. We went from 3 to 9, which is 6. We are now going to do the work for that, which is the dot product of those two vectors, and we get 26. There's no units of measure given in the problem, so there's no units of measure in the answer. But let's look at this second one. This one has more information on the units. It says that there is, a man is pulling a wagon. Now, I want you to think about the fact that a wagon has a handle. And so it's kind of like you got this box and you have a handle that's going like this. But the person pulls the wagon this way. But this right here is a type of vector that's happening. So the situation, the way it looks like, is a little bit different. But the main thing is we have a force vector of 20 pounds, and it's at an angle of 60 degrees. So that's the handle, which means our force vector has a magnitude of 20 and an angle of 60, which we need to find the components for it. So we use our trigonometric form, and we find our vector. So this is the vector for force. This is the force vector in component form. For the displacement, we moved it 100 feet, and it went straight this way when it went 100 feet. And so the angle for that is 0 degrees, which means our displacement vector has a magnitude of 100 and an angle of 0, and therefore the component form for that displacement is 100, 0. We could use that with trigonometric form to figure it out. Now we're going to find the work done on the wagon. We want to know what work was happening, what effort was being put. We do the dot product of force and displacement, and we get the number 1,000. The units of force were pounds. The units for displacement were feet. So this is called 1,000 foot-pounds of work. You have a handout to do that's to practice the concepts we did. And I want you to concentrate on right now on these last three before you even start the handout. Write down on this handout the formulas for each, how you find the dot product, how you find work, and the dot product theorem. So each one of these will have some givens, and then don't forget that the dot product theorem, we have a second part of it is how we use it to find theta. But the dot product theorem does start off with the dot product is equal to, and you can look back in your notes to fill each of these out.